G'day, in this video we're going to start applying all the concepts that we've been learning in Module 6 to understand how DC motors work. This video is going to be covering syllabus content 6.4.1 and 3. We're moving into our final inquiry question, which asks, how has knowledge about the motor effect been applied to technological advances? Primarily, we're focusing on dot point number 1, which is looking at the operation of a simple DC motor. We're going to be looking at some of the components and their functions. We're going to be looking at the torque, which is applied to the coil. We're going to start talking about some of the effects on back EMF, which is also connected to dot point 3 of this inquiry question, which gets us to relate Lenz's law to the law of conservation of energy, and we'll be applying that to a DC motor's context. So our key learning intentions for today, we're going to be able to explain how the motor effect is applied in a DC motor. We're going to explain in particular a particular part that's called commutators and brushes, and how these work to make sure that motors continue to rotate in the same direction. We're then going to look at some quantitative relationships that we can use to calculate for torque in a DC motor. And at the end, we'll look at Lenz's law and the law of conservation of energy and apply that to our DC motors concepts. So effectively, what we're looking at to begin with is this idea of the motor effect, and that being the driver for a DC motor. So as we've talked about before, if we have a charge moving through a magnetic field, or a current that's moving through a current carrying conductor inside a magnetic field, what can happen is that a force can be applied onto that object, which is perpendicular to both the current and or the velocity of the charge, and as well as perpendicular to the magnetic field. So what we have in our diagrams here is a very basic setup to show how a simple DC motor actually works. So let's say there is an electromotive force, a potential difference, maybe caused by a battery or some sort of power supply, that is running through this coil that is in the middle of the magnet. What that means is that we have current running up. We also have current which is heading down the wire, which is running alongside the southern magnet. We could also say that this is going into and out of the page respectively. We also have a magnetic field running from north to south. We should be able to appreciate that this magnetic field is perpendicular to the current going in and out of the page. So in this scenario, we have a current carrying wire, which has current flowing perpendicular to a magnetic field. This is going to lead to our motor effect. Some sort of force is going to be experienced by both of these wires. Now, using our right-hand rule for the motor effect, we should be able to determine that the part of the coil on the left is going to experience a downward force, which again is perpendicular to the current and the magnetic field. And on the other side, using our right-hand rule again, we should find that this wire, or this part of the coil, is experiencing an upward force. What this is going to do is cause the coil to turn. And if that coil is sitting on an axle, which is kind of being shown with the grey dotted line in the center, this is going to cause a rotation. And that rotation is going to allow the electrical energy that is running through the coil to be converted into some form of kinetic energy. And we can harness that kinetic energy for all sorts of applications. I'm sure you can think of many devices which rely on the conversion of electrical energy to form kinetic energy. These are essentially all done by motors. However, with the setup that I've shown you here, there's actually a little bit of an issue. And generally speaking, this is not how we actually wire up a DC motor. I'll show you why. So what I'm trying to show here in the second diagram is a 180-degree flip. So let's assume here that our coil has rotated in an anti-clockwise direction and it's gone for a full 180-degree turn. What that would mean is that our length of wire that is on the left in the first diagram ends up on the right-hand side, and the one that's on the right-hand side ends up on the left. Now, this scenario is not actually particularly productive for a motor, as if we were to apply the right-hand rules, we will see that the forces essentially have flipped on both sides. That on the left, we now have a force which is going upwards on that left wire, and the right wire will be experiencing a force which is pointing down. What this force is going to try and do is slow down the coil as it was starting to rotate and actually force it back in the opposite direction. So rather than having the coil rotate in one direction over and over and over again, think, how a fan behaves. In this scenario, we'd have an oscillation between flipping from 180-degree rotation and back again. This is not how DC motors actually work, and there's a key component that is missing from our diagram that stops us from having a functioning DC motor which rotates in one direction only. This is essentially a commutator. Now, generally speaking, commutators are represented sort of like this, or this, or this in a diagram. They are a split ring, which is a conductor that is able to essentially flip the direction of the current which is running through a coil in a motor. We also place brushes on the ends of the circuit where the commutator is sitting in between, and those brushes allow for electricity to pass into the commutator and through the coil. I'd like to explain how commutators work using this diagram here in particular. I want you to look at the setup as it is right now. We have current which is running from the right side and back through to the left. This is going to induce a torque. In particular, the coil is going to start rotating clockwise. And as it starts to rotate, we'll see that both halves of the commutator are still in contact with the brushes. There is electric current still running through, but we are going to get to a point where there is a full turn and the commutator flips. Each brush is now in contact with the other commutator. And what we should be able to see is as that turns over, the current running through the commutator flips. So instead of current going from K to L like it does in the first two images, we now have current going from L to K. And when that flips over, what that means is when we get back to this flat scenario, we can actually see that current is still running in an anti-clockwise direction around the loop. However, technically, the current is actually going in the opposite direction because we've got that 180 flip happening in the loop. What this allows for is for when the coil is sitting flat and you've got the magnetic field running across it, we have a scenario where the left-hand side is always going to generate an upward force and the right-hand side is always going to generate a downward force, causing, in this scenario, the coil to be able to continuously rotate in a clockwise direction. This would not be achieved without having a split ring commutator which is able to flip the direction of current which is running through the coil at every half turn. If it didn't exist, again, we would have a scenario which looks a little bit more like this, where the forces applied to the left and right hand side of the coil continuously flip every 180-degree turn. What I want to look at next is the torque generated in a DC motor. We talked about torque in Module 5, and that described rotational motion. It's come back again here, and this is simply because our coil is rotating in a circular motion. Therefore, there is torque which is generated. And torque can be defined using this formula here, that torque is equal to NIAB sine theta. It seems to be a little bit of a mix of a few formula that we have encountered before, and I want to go through a process to show you how that formula actually comes to be. What I want to do first is look at our original torque formula, that torque is equal to radius times force times sine theta. In particular, I'm going to be paying attention to the radius and the force. Torque can be determined if we know how much force is being applied to the object and how far away it is from the point of rotation. So for a DC motor, the radius is essentially the distance between where the force is being applied on the wire and the point of rotation, which is the center line which runs down the coil. So R exists on both sides and they are equidistant from each other. If we reflect on the width of the coil, let's call that the dimension that goes from left to right, our width, we can write a little bit of an equation here which describes the relationship between the width of the loop and the radius for torque. And that relationship is obviously quite simple, but it will be helpful to us in a moment when we start looking at combining some formula. The second formula that we've got here is that F is equal to LIB sine theta, and that describes the force which is applied to a current carrying conductor when it's in a magnetic field. So I is pretty straightforward. That's the magnitude of the current that is running through the wires on the left and the right of our coil. B is the magnitude of the magnetic field. L is a little bit interesting, and it refers to, in particular, the length of the conductor which is experiencing the force due to the magnetic field that it's exposed to. So that essentially is the opposite dimension of this square with the loop that we're working with. One more detail that's really important to take into account is that there are actually two forces being experienced, which are both contributing to the torque around the coil. There is a force which is being experienced by the first wire running perpendicular to the magnetic field. We also have a second force, which is equal in magnitude but opposite in direction, and that's for the second wire, which is also perpendicular to the magnetic field. Now what that means is that force 1 is equal to LIB sine theta, and force 2 is also equal in magnitude to LIB sine theta as well. So what that means is we can say that the total force is equal to force 1 plus force 2. Even though they're going in opposite directions, both forces are contributing to the same torque. So we can say that that is equal to LIB sine theta as well. But because they're additive, we're actually multiplying all of that by 2. So if we know that torque is equal to RF sine theta, we can substitute in for R and F respectively. The radius is going to be the width of the coil divided by 2, and the force which is applied to the coil is going to be F total. The total torque that's experienced by the coil depends on the force which is applied on the left-hand side as well as the force that's applied on the right-hand side. So that's going to be equal to 2 LIB sine theta. At this point, what I'm going to do is separate some of the terms so that we can come up with a little bit of a cleaner equation. So what I've done here is separate out all of the terms that have got to do with the dimensions of the loop. And by cancelling out these 2's here and recognizing that length times width is essentially area, we can say then that torque is equal to AIB sine theta. So the amount of torque generated will depend on the area of the loop. The larger the area, the greater the torque. I, our current, as well as the strength of the magnetic field. And then you've also got sine theta, which I'll come back to in a moment. However, what you'll notice is that this formula is not identical to the torque formula in your data sheet. It includes N, which, as we know, is our number of coils. The formula that I've derived here works for a single coil, but if you were to have 2 coils, the torque would be doubled because both coils would be experiencing that same torque and the total torque would be additive. This pattern would go on and on and on. Essentially, every coil that you add, you're going to get the same amount of torque for a single coil added on top. So there we have it. Torque is equal to NIAB sine theta, where theta is equal to the angle between the A vector, or the area vector, which is essentially like a normal perpendicular to the area plane, and the magnetic field. Last concept I want to talk about today is Lenz's law and back EMF. We already know that Lenz's law applies the law of conservation of energy, and the general gist of it is that the direction of electric current which is induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes changes in the initial magnetic field. What I want you to appreciate is the idea that if you've got a loop rotating in a magnetic field while it's rotating because of the motor effect, you will still induce a back EMF. As we've talked about previous, any change in flux for a conductive material will lead to the generation of some sort of current. And that current is going to be dictated by a back EMF because we're going to end up producing a magnetic field that works against the inducing magnetic field. And this will occur even when the object is moving through a magnetic field due to the motor effect. So what that means is in a motor, you've got back EMF and friction, which are existing as resisting forces. And what this actually ensures is that we're not continually adding more and more and more motion to the coil. Instead of accelerating infinitely, what we'll end up having is the coil reaching a stable rate of rotation. So that can sort of be explained because if you have more rotation, there's going to be more change in flux in the coil. If there's more change in flux, you're going to generate a larger back EMF. That back EMF is going to reduce the current that's running through the coil, and eventually you're going to hit this equilibrium point where the current through the coil is going to stabilize, and essentially the rotation of the coil is going to balance out with the resisting forces. So you won't have any more acceleration, but the resisting forces won't slow the coil down any further than what it already is. And that's all for now. That's our DC motors basics. We're going to spend a fair amount of time in class breaking down some of these core concepts. But the next time we have a video, we're going to be looking at DC and AC generators. They work quite similarly. However, rather than having a current running through a coil and generating a force, instead what you'll have is a coil which is rotating around a magnetic field that leads to electromagnetic induction, producing electric current. But until the next time, have a good one.